Hi, and welcome back to another video on the series for 8086 microprocessor. In our last video, we spoke about how to interface memory devices to a microprocessor. This time I thought we should discuss how input-output ports could be interfaced to the 8086. So let's look at how one could really access an input-output port as far as the 8086 is concerned. So if you look at this, there are memory devices, and we've discussed this in the past. The memory devices are really connected to the processor through data buses. And of course, they have control and address lines that come into the memory device. Similarly, you could have an input device, and the input device would have a data bus that goes into the processor. It will for sure have address lines because you need to address that input device, something like a keyboard. And of course, the input device needs control signals. Similarly, you could have an output device, and the output device gets data from the processor. So it's the other way around. The input device gives data into the processor. The output device gets data from the processor. It also has control lines, and it has address lines. And the processor really doesn't care whether these are memory devices or I/O devices. As long as the processor gives or gets data at the time that it needs it, it's really just another source of information for the processor. But there are various techniques for accessing such I/O devices. The first one is called a memory mapped I/O. So what does a memory mapped I/O mean? All of us by now ought to know about the 1 megabyte of memory space that the 8086 can access. You of course connect the data and address bus to this memory space. In the memory space, you have specific regions like the absolute low end of memory starting at 00, which must have memory to manage the interrupt vector table, and absolutely top end of the memory space at 0FFFF0, at which the processor starts executing instructions when it gets a reset, that must have physical memory. Anywhere else in that 1 megabyte space, it could be memory located at whichever address you choose to place it. For a memory mapped I/O, in addition to these physical memory devices, you also have the I/O devices, and they are also placed in the same memory space, in the same 00 to FFFF hex. Now, as far as the processor is concerned, what it means is that to access these I/O devices, the input-output or I/O input-output device, all it needs to do is use the same set of instructions, which is the MOV instruction, that it would use with a normal memory device. So what you have done as a designer is told the processor, you know what, some of my devices are memory and some of them are input-output ports, but as far as you are concerned, everything is memory. And please use the MOV instruction to access inputs from input devices or to write outputs to the output device. This is called memory mapped I/O. Let's contrast this with the I/O mapped I/O. In this case, what happens is you have a memory space which is 1 megabyte. In addition, you have another 64 kilobytes of input-output space. There's a separate address map completely different from the memory address map. And the data bus is still the same, so because the processor of course has just got one data bus. So both the data buses of the memory devices and the I/O devices are connected to each other. The address lines are the same. Again, remember the processor just has one set of address lines that come out of it, so both the memory devices and the I/O devices are connected to the same address lines. What differentiates the two is that in the case of a memory, the memory read-write control signals are used, whereas for an I/O device, there is an I/O read-write control signal. There's a separate set of signals that the microprocessor generates to control I/O devices. Now, if you wanted to access the memory device, how do you know how does the processor know whether to generate a memory control signal or an I/O control signal? The way you do that is by pulling the line M/IO bar low. And if you pull it low, it means it's an IO instruction. If you pull it high, it means it is a memory instruction. That differentiates the two. So M/IO bar pulled high, you have to use the MOV instruction because it's a memory space that is being accessed. M/IO bar pulled low means IO is active and you have to use the in or out instruction of the assembly set. This is how IO mapped IO works. So you've got memory mapped IO where the IO devices rest in the same memory space as regular memory. You've got IO mapped IO in which there is a separate space of 64 kilobytes specially designed for use by the in and out instruction. This is an example of an IO mapped IO. What you see now here is a set of keys that are connected to the processor using an octal bus transceiver, the 245, 74LS245. This information is written or read over the data bus, right? That's what we said earlier as well. The IO read signal is active in this case because this is an IO mapped IO. So whenever you wanted to read the status of the switches, you needed to activate IO read. And when you're activating IO read, you also need to decode, basically to generate a chip select, you need to decode a set of address lines that constitute the chip select. This is the way you would map an IO device to your processor. If you now wanted to add an LCD display to this, for example, so what did we say? We said there are a set of switches, which is connected through the octal bus transceiver, and a combination of address lines and IO read lines tells the processor when the information is to be read from, whenever the information is to be read from the switches, and that information is available on the data bus. In addition to this, you have the LCD displays. So this is now an output device. Remember, the switch was an input to the processor, and LCD display is an output from the processor. So the output device is enabled by a decoder which converts BCD to 7-segment display. Right? So BCD is just binary coded decimal. That gets converted to a 7-segment display by the BCD to 7-segment display decoder. This is enabled by the address lines PA0 to PA3, and in addition, you have to use a latch using the IOW, the input-output write signal, to enable a latch that latches the data that will be used to be displayed on the LCD display or the LED display. This is an example of both an input, which is the switches, and an output, which is the LCD display, being connected to a processor in the IO mapped region using IO read or IO write.